have a final exam?
Yeah, we just can't, unfortunately. I would have liked to. I mean, I normally do a fourth exam and a final, but we don't have time. I mean, we again we missed nearly 2 weeks of class time, um, and it's not possible. We've only got 4 meetings left before the last day. So there's today, 19th, 21st, 26th. So there's just no time to do it. And scheduling outside of class time is too difficult. So, uh, I've complained to people in the past saying that the way we schedule calculus 2 and 3 in the summertime always gives us this problem. And it's not a good thing, because we're really cutting things, we're really rushing through it and missing a significant amount of instructional time. But, every time I say it, people are just like, eh. So what can I do? I'm sure you'll encounter this many times in your life. So me, what does he know? So anyhow, um, I will have a study guide for you for the fourth exam. Okay, and I'll give you tell you exactly what's going to be on it. So I'll have a study guide, and I'll tell you exactly what's going to be on the exam. I mean, not the problems themselves, but I mean exactly what problems to expect. Okay, so last time we left off with the end of section 6.2 on line integrals. So we left off with number 92, I guess it was, 92. And so today, and that was the last problem for section on the list for section 6.2. Is there any others that are just sort of screaming out to me like we should do this one? Let me see. Let's check out 82. Look at 82 here. So in number 82, so we want to calculate the line integral x times y to the fourth dx. That's the scalar line integral. Over c, where c is the right half circle, x squared plus y squared equal to 16. So the half circle like this. So of radius 4. So by the way, on the exam, I'm not going to like give you the parameterization of the curve. I want to have you guys pick the parameterization. So for a circle, for a line segment, or something of this sort. Um, so and again, remember, there's often different ways to pick parameterizations, but it doesn't matter. Whichever way you choose it, you will always get the same answer. So let's do this with two different parameterizations. So solution 1. So the obvious thing to use when you're talking about circles is we'll circle of radius 4, is 4 cosine t for sine of t. And then this will be for minus pi over 2 less than or equal to t less than or equal to pi over 2. That is the definition of sine and cosine, right? They're the x and y coordinates on the circle of radius 1 for angle t, or angle theta, or whatnot. But if it's not radius 1, if it's radius 4, you just multiply by 4. Okay, so that's r of t. R prime of t is minus 4 sine of t, 4 cosine of t, and then the length of r prime of t is going to be equal to, well, it's just 4. Right, it's the square root of x squared plus y squared, but it just gives you 4. F of xy is xy to the 4th. So now f of r of t, that's the function along the curve r of t. The x is 4 cosine t, and the y to the 4th is 4 sine t to the 4th. So this is going to be equal to 4 to the 5th, which is 1024, cosine t sine to the 4th t. So there's all the ingredients for doing the calculation. All right, so the integral over c of xy to the 4th ds is equal to the integral from a to b, so we'll just write it all out, f of r of t times the length r prime of t dt. Right, so here, what do we got? We got the integral from minus pi over 2 to pi over 2. F of r of t is 1024 cosine t sine to the 4th t times 4 dt. So 4 times 1024, it's 4096. Integral from minus pi over 2 to pi over 2 cosine t sine to the 4th t dt. How would we do this integral, this antiderivative? Does anyone see how that's going to go? Let's see how that works. It's a u substitution. You just let u equal sine t. So du over cosine t is dt. So it's 4096. Integral from minus pi over 2 for sine is u equal to minus 1 to u equal to 1. Cosine t, u to the 4th du over cosine t, so those go away. So 4096 over 5 u to the 5th, from minus 1 to 1. So that's 1 plus 1 is 2. So that's 8,192 over 5. Is that times 2 there? 180, 192, yeah. So that's solution number 1, picking that sort of obvious parameterization, the obvious parameterization for the circle using sine and cosine. Right? That's just the definition of sine and cosine, and so, that's why it gives us what we're looking for there. You can take that to be the definition of sine and cosine, the coordinates upon the unit circle, or you can use that right triangle definition, using a right triangle with hypotenuse of length 1. but it's the same thing. Okay, solution number 2. So in this case, how else can we parameterize a circle? Right, well, with the circle, you have x squared plus y squared is equal to 16, right? So you can also write this as x is equal to the square root of 16 minus y squared. Right, because it's the right half. So instead of y equals 16 minus x squared, it's x equals 16 minus y squared. Anytime you have a curve, so remember this sort of standard parameterization. So given a function y equals f of x from a to b, so this is y equals f of x from a to b, a standard way to parameterize this would be r of t equal to t f of t, a less than or equal to t, less than or equal to b. Right, so you just call x t, and y is f of t, and that's it. So that's what we're going to do here. Of course, this is a function x equals f of y, but same kind of idea. It's a minus 4, by the way. So this becomes r of t equal to 16 minus t squared t minus 4 less than or equal to t less than or equal to 4. So this is r of t now. So r prime of t is equal to, well, the derivative of this is minus t over the square root 16 minus t squared, 1, comma 1. And the length of r prime of t, well, it's the square root of this squared, t squared over 16 minus t squared plus 1 squared. And when you actually simplify this expression, this becomes t squared plus 16 minus t squared over 16 minus t squared, and you get 4 over square root 16 minus t squared. Okay, so it does simplify a little bit there. So now f of xy is equal to xy to the fourth. So in this case, it is t to the fourth, or so f of r of t equals t to the fourth, and then x is 16 minus t squared. This. So so the integral over c of x y to the fourth ds is the integral, right, from a to b of f of r of t, length r prime of t dt. Right, so it's the integral from minus 4 to 4. F of r of t is t to the fourth, 16 minus t squared, the length of r prime of t is 4 over square root 16 minus t squared. Lo and behold, that ugliness goes away. Right? It just cancels right out. So it's just 4t to the fourth. So this is just becomes 4 times integral from minus 4 to 4, t to the fourth dt. All right, so that's 4/5 t to the fifth from minus 4 to 4. 4 to the fifth is 1,024. Minus 1,024. So it's 2,048 times 4, so 8,192 over 5. Same answer as before. Right? Right, so that's a real nice example of just the scalar line integral. Okay, real nice example of the scalar line integral. For sure, absolutely, we will have one problem where I'll ask you to calculate a scalar line integral on exam 4. Okay, so I mean, throughout this chapter, there's several integrals that are going on. First, we start out with the scalar line integral, then we do the vector line integral, then we'll do the scalar surface integral, and then the vector surface integral. So there's 4 integrals. For the scalar line integral and the scalar surface integral, there's no shortcut to calculating it. You just calculate it as a straight calculation like we're doing here. And that's all there is. That's all there is. Can't do anything else to it. There's no way to simplify it. With the vector line integral and the vector surface integral, there is the fundamental theorem of calculus for line integrals. There is Green's theorem. There is Stokes' theorem. There is divergence theorem. So for the vector integrals, there's direct calculation and then calculation through these theorems. Right? So we're going to have various questions on those. But for sure, there's going to be one scalar line integral on the exam, and I will ask you to parameterize the curve. I won't give you the parameterization. I'll ask you to parameterize. All right, let's see. Is there a vector line integral that's just screaming out to be solved here? Yeah, let's check out 77 there. So in 77, so this is that other notation for these integrals that I don't like too much, but anyway, whatever. So for 77, so by the way, when they write p dx plus q dy over c, means same thing as p q dot dr. It seems like the book prefers this notation. Anyway, they're both the vector line integral. So in this one, calculate line integral over c, x squared dx minus xy minus x squared, or wait a minute, I was wrong. What is that? Y squared dx plus xy minus x squared dy. So that's the line integral over c y squared xy minus x squared. Oh, is that a minus? It's a plus. Should be a plus. Dot dr, where C is y squared equals 9x from 0, 0 to 1, 3. So from 0, 0 to 1, 3. Y squared equals 9x from 0, 0. Right, so x is equal to 1. If x is equal to 1, right, y squared equals 9x. 1, 3. So they mean if x is equal to 1, this is 9. Oh, no, that's right. I'm sorry. From 0, 0 to 1, 3. In this direction. Now, with the scalar line integral, or the vector line integral, okay, you have to pay attention to direction. I'm sorry, this is not the curve. It's this. Parabola is opening the other way. Okay, so here we have so 1/9 y squared is equal to x. So again, x is equal to f of y. So you can pick this standard parameterization. So normally I would do like a y equals f of x. Well, what you can do, we could do it that way if you want. Either way, so you get y is equal to 3 square root x. Right, so you got y is equal to f of x. So you pick this standard parameterization. X is equal to t, and then y is equal to f of t. And it's from x equals 0 to x equals 1. 0 less than or equal to x less than or equal to 1, right? So anytime you have a curve defined by y is equal to a function of x, or x is equal to a function of y, you can just, put x equal to t, y equal to f of t, or y equal to t, x equal to f of t, whichever is the appropriate thing. And then the bounds are just the bounds for your variable. X goes from 0 to 1. Or if you're doing it in terms of y goes from 0 to 3. Right? So there's that. And you could pick either parameterization here. I could do like x equal to t or do y equal to t. It doesn't matter. If you pick two different parameterizations, it'll give you the same answer. One calculation might be easier than the other, but you'll still get the same answer. All right, so that's r of t. So now we need to know r prime of t. So r prime of t is just t and then 3 halves t to the negative 1/2, like that. And f was equal to f of xy was equal to y squared xy minus x squared. So the f of r of t is equal to y squared, so that's 9t, xy, so that's 3t to the 3 halves, minus x squared, that's just t squared. Right, x times y is 3t to the 3 halves. All right, so that's f of r of t. So now the integral, that vector line integral, the work-related line integral, is equal to the integral from a to b f of r of t dot r prime of t dt. Right? So this is the vector line integral calculated, with a straight calculation, not using the fundamental theorem of calculus, not using Green's theorem. Actually, you can't use the fundamental theorem of calculus here because it's not conservative, this vector field, right? This is P, so the derivative of P with respect to Y is 2Y, and the derivative of Q with respect to X is Y minus 2X. So they're not the same, so it's not conservative. Nor can you use Green's theorem. Can't use Green's theorem to calculate because it's not a closed curve. For Green's theorem, you need a closed curve. So it's just a straight calculation of the line integral. So in this case, it's the integral from 0 to 1. F of r of t is this right here. 9t, comma, 3t to the 3 halves minus t squared dot r prime is t 3 halves t to the negative 1 half dt. Now, probably it would have been easier to use a parameterization that doesn't have the square root in it, so we don't have to deal with these fractional exponents, but it'll be fine. So dot product is 9t squared plus 9 halves t squared right, 3 halves t to the negative 1 half times that. Oh, no, 3 halves minus 1 is just 1. So 9 halves t minus 3 halves t to the 3 halves dt. All right. Antiderivative, 9/3. So that's 3t to the third plus 9/4 t squared. Adding 1 to this, you get 5 halves to 2/5 minus 3 halves times 2/5 t to the 5 halves from 0 to 1. So that's 3 plus 9/4 minus 3/5. So it's 3 plus, so 45 minus 12 over 20. So 45 minus 12 is 33 over 20. So 60 plus 33 over 20, so 93 over 20. Let's check the answer. Make sure we get that right. Six 6.15. 6.15. That's not right. I don't think what I got. What was it, 30? No, 93 over 20. 4.65. Something is off.
When you were doing the initial calculation for the derivative of r, why didn't you change the t?
Why did I what? Sorry?
Like the r, it's
Mhm.
equated to t, but like when you did the derivative, it stayed as t. Wouldn't that turn to 1 instead? If you did the
Oh, yeah,
derivative?
that's supposed to be a 1. Very good. So, where is that? That's a 1 right there. So that changes this here to 9t. So this becomes 9 halves t squared. Oops, t squared. So this is a 9 halves here. So let's redo that. So over 20. So multiply this by 10. 90, this one by 5, plus 45 minus that one by 4, 12 over 20. So 135 minus 12 is 123 over 20, which is 6.15. Yeah. Right, because 120 over 20 is 6, and 3 over 20 is 0.15. Okay, so that is a scalar line integral calculated just directly. Or sorry, a vector line integral calculated directly. I'm not sure if I will have that on the exam 4. I might. But I mean, that's one type of problem you can get. So now moving on to the next section, the fundamental theorem. Section 6.3. The fundamental theorem of calculus for line integrals, right, which is the following: the line integral over C, where C is any curve from AB to, I should use C twice, to PQ, something like that, in this direction. Okay, the line integral over C of a gradient vector field is equal to f of, and this can be over two dimensions or 3 dimensions. I'm writing it over 2 dimensions here, 2 variable function, but it works just as well for 3 variables because it just follows from the chain rule in the ordinary fundamental theorem of calculus. It's just fxy from PQ to AB for a gradient vector field. So it doesn't matter what the curve is, right? It just matters where the curve starts and where it ends. So there's different ways to calculate it. If you want, you could take like the straight line between those 2 points and calculate the line integral directly over the straight line, right? That would be one way to do it. Or just to find the antiderivative of the gradient vector field and plug in the beginning and the end. Either way would work. And of course, if the curve is closed, if it's a closed curve, then this is 0. Like if the starting point is the same as the ending point, then that's going to be 0. So there was a problem from the last section that really belongs in this section, and that was number 84. So evaluate f dot dr, where f is this, and c is any path from minus 1, 0. Oops. There we go. From minus 1, 0 to 5, 1. So what do we have here? 2x sine y. X squared cosine y minus y squared minus 3y squared. So calculate this, where C is any curve going from minus 1, 0 to 5, 1. Now, the way that the question is being asked is, basically hinting at the fact that that's got to be a conservative vector field. So it has to be a gradient vector field. So, let's check it out. So right here, this is P and this is Q. So Py is equal to 2x cosine y, and Qx is 2x cosine y minus 0. Right, so they're the same. Right, so they're conservative. So the vector field is a gradient field. So let's find it, right? So finding f of x, y, this means this p is the partial derivative with respect to x, is 2x sine y, and q is the partial derivative of f with respect to y, which is x squared cosine y minus 3y squared. So here, the antiderivative with respect to x is x squared sine y plus some function that just uses y, right? Because that's the arbitrary constant when you're doing the partial derivative with respect to x. It's just a function in terms of y only. Here, the antiderivative with respect to y is x squared sine y minus y to the third plus h of x. Right? So here you could just pick fxy to be that with no h of x at all. So choose fxy equal to x squared sine y minus y to the third, right? Which now satisfies both. Both this and that. Right, so g of y is y to the third minus y to the third, and h of x is just 0. So this line integral is equal to x squared sine y minus y to the third from 0, negative 1 to 1, 5, right? Or negative 1, 0 to 5, 1. So you plug in 5, 1, and you get 25 sine 1 minus 1 minus plugging in x equal to negative 1, y equal to 0, you just get 0. So 25 sine of 1 minus 1. Okay, so that's the example there. Moving on to the problems in section 6.3 itself. So the first one is 105. Oof, that's a nasty looking one. Seriously, what the heck? Evaluate that line integral f dot dr, where f is this, and c is the path from here to there for t from 0 to 1. I mean, it's going to take me forever just to copy that down, but I wish this would go away. There we go. It looks worse suddenly. So f is e to the x sine y minus y. And then e to the x cosine y minus x minus 2. So this is f. So this is p, this is q. So p is supposed to be the antiderivative with respect to x is e to the x sine y minus y. So the antiderivative with respect to x is e to the x sine y minus xy plus g of y. Right, that's the arbitrary constant. And then q is e to the x cosine y. And q is supposed to be partial derivative with respect to y minus x minus 2. So this says that f is equal to e to the x sine y minus xy minus 2y plus h of x. So what is a function that matches both of these? If there is no such function that matches both, then you know it's not a conservative vector field. But here, it better have one. So we have e to the x sine y minus xy in both. And then plus g of y, so that'll be 2y. And then h of x is 0. Right, because there's no h over there. So the integral over, and then r, what is c? So now c is r of t equal to something. T to the third sine pi t over 2 comma pi over 2 cosine pi t over 2 plus pi over 2. So it's pi times t plus 1. So pi over 2 cosine, or minus pi over 2 for t between 0 and 1. Now, of course, that's a really nasty looking r of t, but all we care about is where we start and where we finish. So r of 0 is what? Well, this is 0. And then this is cosine of, so t plus 1 is 1. So cosine of pi over 2, which is 0. So r0 is 0. And then R1 is equal to what? 1 times sine pi over 2 is just 1. And minus pi over 2 cosine 2 pi over 2 is cosine pi. That's negative 1. So you get negative 1 times negative pi over 2 is just pi over 2. So this is the start, and this is the end. So the line integral over c of f dot dr is just equal to this antiderivative, e to the x sine y minus xy minus 2y from 0, 0 to 1 comma pi over 2. So at 1 comma pi over 2, so x is 1, y is pi over 2, this is going to be e to the 1 times sine of pi over 2 is 1, minus pi over 2, minus 2y, and then minus at 0, 0, these are all just 0. So it's e minus 3 pi over 2. I believe that's got to be correct. Yeah. Okay. So the fundamental theorem of calculus for line integrals that, I mean, it takes as long as you can apply it, it might be the easiest way to go about doing a line integral calculation. So that's 105. 107. So 107 just, determine whether it's conservative or not and find the potential function. The potential function is the antiderivative, gradient antiderivative, whatever you want to call it. So 107, we got minus y e to the x sine y. Plus e to the x. And then x plus 2 e to the x cosine y. All right, conservative or not. All right, well, this is p. So we look at the partial derivative of p with respect to y, and you're going to have minus 1 plus e to the x cosine y, and the partial derivative of q with respect to x is going to be equal to, I got to use the product rule. So it's the derivative of x plus 2 times e to the x cosine y plus x plus 2 times e to the x cosine y. The derivative of x plus 2 is 1, and the derivative times e to the x cosine y plus x plus 2 times the derivative e to the x cosine y, which is just e to the x cosine y being a constant. So these are not equal at all, right? So this is x plus 3 e to the x cosine y. So these are not equal. So not conservative. Right? Not conservative or not a gradient vector field. So that's 107. 109. 6x plus 5y, 5x plus 4y. Five x plus 4y. All right, so the derivative of p with respect to y is 5, and the derivative of q with respect to x is 5, right? So this is conservative. So since it's conservative, we should be able to find the antiderivative, or the potential function. So f, partial derivative of f with respect to x is going to be p. So that's 6x plus 5y. So f is going to be the antiderivative with respect to x, 3x squared plus 5xy, plus g of y. And then partial derivative of f with respect to y is 5x plus 4y. So f, the antiderivative here with respect to y, is 5xy plus 2y squared plus h of x. So we have a 5xy in both. Right, so here's 5xy, here's 5xy, here's 3x squared, and here's h of x. So h of x is 3x squared. And then here's g of y, and here's 2y squared. So there's your potential function. All right, so that function f, its gradient field, is the one we started with here. All right, so it's 7:27. Let us take a 5-minute break. So let's come back at 8:35 or so. Okay, so we'll restart at 8:35. Hi everyone, we're back. Okay, so that was number 109. So now 113. For the following exercises, evaluate the line integral using the fundamental theorem of line integrals. Sometimes they put this little circle on the thing, on the integral symbol, and it's just decoration as far as I know. So I don't know, maybe it means conservative or something like that, but I don't think it means anything. So 113, 2y dx plus 2x dy. So this is 2y dx plus 2x dy. So this is f dot dr, where this is f. And c is, well, I mean, they say the line segment from 0, 0 to 4, 4. But I mean, it can be anything. So let's do it in two different ways. So let's do solution 1 with the fundamental theorem. All right, so with the fundamental theorem, so partial derivative of f with respect to x is 2y. So f should then be equal to the antiderivative with respect to x, just 2xy plus gy. And then fy is 2x, so the antiderivative of that with respect to y is 2xy plus h of x. To match this function, these two expressions for the same function, we just have fxy equal to 2xy, and then g and h are both 0. Right, so the integral over c of 2y comma 2x dot dr is equal to the integral from, the antiderivative 2xy from 0, 0 to 4, 4. So this is 2 times 4 times 4 minus 0, so 32. Okay, so that's one solution. Solution 2, let's just pick a curve from 0, 0 to 4, 4. We'll just make it the straight line. Right, so of course, again, we're going in this direction, but then we'll just pick the straight line from here to here. So the vector along that straight line segment is just the vector 4, 4. The parameterization of that line is just the base point, 0, 0. So 0 plus 4t, comma 0 plus 4t, 0 less than or equal to t less than or equal to 1. Right? Remember that standard way of parameterizing the line segment. Come on. All right. So now that's r of t. So r prime of t is just that slope vector 4, 4. F is equal to 2y comma 2x. So f of r of t is just equal to the vector 8t, 8t. So now this line integral over c, right? The fundamental theorem of line integrals, it says that the value of the line integral is the antiderivative at 4, 4 minus antiderivative at 0, 0, where 4, 4 and 0, 0 are the beginning and the end. So the curve doesn't matter, just that it's a continuous curve from beginning to end. So if you want to pick a curve, so that means it's path independent, as they say. The answer is independent of the path from A to B. It's just depends on A and B. So if you're going to use a path, you might as well pick the simplest one, the straight line. And that's what we did. So this is equal to the integral from A to B of f of r of t. Now just doing a straight calculation of this vector integral. So this is the integral from 0 to 1. F of r of t is 8t, 8t dot r prime is 4, 4 dt. So this is 4 times 8, 32, so that's 64t. So this is 32t squared. The antiderivative from 0 to 1 is 32. Same answer, right? Same answer. So, I mean, if I asked you such a question, you could take either approach. You could calculate the line integral on a straight line from point A to point B, or you could, find the antiderivative, or potential function, the function whose gradient field is that vector field. 117. So for the following exercises, determine whether it's conservative. This is just like the other ones that we just did. Let's do one. So on your own, 117 on your own. But let's do number 119. Is that the one that's assigned? Yeah, 119. Or 120, 119 and 122. So these are three-dimensional vector fields, all right? And a three-dimensional vector field, a test for being conservative involves calculating the curl. So they don't call it the curl in this section, but when you calculate the curl and the curl is 0, you know it's conservative. Conservative vector fields in 3 dimensions have 0 curl, and having 0 curl implies conservative. So it's a logical equivalence when you have, continuous partial derivatives and all that. But all the functions we deal with are usually continuous. So, checking that is kind of annoying. You could just assume it's conservative and find the potential function. If you fail to find a potential function, well, either you made a mistake or it's not conservative. So let's check it out. Let's do the curl. Why not? So the curl is in the next section, but, we can do it here. So 119, so we have y e to the z, x e to the z. And then x, y, e to the z. Right, so the curl of f is the 3x3 determinant I, j, k with these differential operators, partial with respect to x, partial with respect to y, partial with respect to z, y e to the z, x e to the z, x, y, e to the z. So, in the x coordinate, it's this 2x2 determinant right here. So partial with respect to y of this, so that's x e to the z, minus partial of this with respect to z, which is x e to the z. In the y coordinate, it's the 2x2 determinant that doesn't use the middle column there. So partial derivative of this with respect to x, which is y e to the z, minus the partial derivative of this, which is with respect to z, the product here and here, which is partial derivative with respect to z, which is y e to the z. And then in the x coordinate, it's that, or the z coordinate, it's this 2x2 determinant. So the partial with respect to x of that, which is e to the z, minus the partial with respect to y of that, which is e to the z. So this is equal to 0, 0, 0. So f is conservative. It is a gradient field. So doing that check, for a three-dimensional vector field is a little bit more involved, and it involves using that curl operation, which is from the next section. But, whatever, we can do it now. We were supposed to have watched that video. I hope you did. But anyway, if you didn't, that's just a check for it being conservative. Now you actually got to find the potential function. The function whose gradient field is this. Okay, so this is P, this is Q, this is R. you know, and then the curl of PQR, by the way, is equal to, so it's that 3 by 3 determinant, J, K, partial with respect to X, partial Y, partial Z, P, Q, R. So if you actually calculate this, it is RY, QZ minus PZ, RX and then plus QX, PY. All right, so it's that. All right, that's the curl. Partial of R with respect to Y minus partial of Q with respect to Z, partial P with respect to Z minus partial R with respect to X, and Q with respect to X minus P with respect to Y. That's the, you know, the check in 2 dimensions, that Z coordinate right there. That's not a coincidence. But anyway, this says that it is conservative. So here, the P is supposed to be F with respect to X, so that's Y e to the Z. F with respect to Y is supposed to be the Q, so that's X e to the Z. And partial F with respect to Z is supposed to be R, so that's X, Y e to the Z. So antiderivative here with respect to X, X, Y e to the Z, plus arbitrary constant, H of YZ. So some function with respect to just Y and Z. It's going to be a constant with respect to X. This one says F is equal to the antiderivative of this with respect to Y, just X, Y e to Z plus G of X, Z. So just some function with respect to X and Z. When you take the partial with respect to Y, that's 0. And then this one, FZ, antiderivative with respect to Z, just got e to the Z there, so it's just X, Y, e to the Z. G, H, I, J, K of X, Y. Right, so a function f, x, y, z, which matches all of those, is just going to be x, y, e to the z. So there's your potential function, and the gradient of that potential function is equal to this f right here, as you can see. Partial derivative with respect to x is that, partial derivative with respect to y is this, partial derivative with respect to z is that. Okay, so same process for a three-dimensional vector field. Finding the potential function, you just have to do 3 antiderivatives rather than 2. You know, and then the check, although it's not a quick check anymore, is calculating the curl of that vector field. And if it's not 0, then you know that the vector field is not conservative. So I think probably in 322 looks like it is not going to be conservative. You got that funny cosine there. Or not 322, 122. So 3z squared minus cosine y. That's the one we're supposed to do, right? 122. Or, where is it? Yeah, 122. So f is equal to 2xy, x squared plus 2xy. No, 3z squared. 3z squared minus cosine y. Minus cosine y and 2xz. So the curl of f, I, j, k, partial with respect to x, partial with respect to y, partial with respect to z, 3z squared minus cosine y 2xz. So this is equal to, so first, this derivative with respect to y is 0. This derivative with respect to z is 0. So that's just 0. 0 minus 0. And then here, this derivative with respect to, well, the negative of this derivative with respect to x, which is 2z, minus this derivative with respect to z is 6z. Okay, so there you go. It's not 0. And then k is this derivative with respect to x, this derivative, that's 0. So this is equal to 0, 4z, 0, which is not equal to 0, 0, 0. Right? So it's not conservative. Not a gradient field. F is not conservative. Okay? If you tried to find a potential function here, then it would fail. You would not be able to find that potential function. Although it may be confusing because you may sort of think, oh, I probably made a mistake, and you go back to it. So maybe it is worthwhile to do that check, I guess. All right. So that was 122. $125. So for the following exercises, determine. We already did that. It's on your own. $130, $131. So 130. Calculate F over C1. So the vector field is given right there. So calculate the line integral of F over C1. And then 131 is calculate the line integral of G over C1 over C1. And both times they're circles. So we'll do 130 here. So F is equal to 2xy squared to yx squared plus 2y. So calculate F dot dr over C, where C is the circle of radius 2 in the counterclockwise direction. Oh, wait a minute. Wait. C1, what's C1? C1 is... Well, C1 is a circle. C2 is that line segment thing. Okay, well, That's a closed curve. So if this is conservative, it's 0. Right, so let's check it out. So P is 2, this is P, this is Q. So Py is 4xy, and Qx is 4xy. Right, so it's conservative. Right, so the integral over C f dot dr is just what? What is it in this case? Right, so it's
0.
it's 0. Right, you calculate the potential function f(x,y), at the starting point AB. So you pick anything to be the starting point AB, and then your finishing point AB. Right, so it's f of AB minus f of AB is just 0. Oops. And then 131, probably it's the same thing, huh? So the derivative of this with respect to y is 1. Ooh, it is not conservative, that one. Okay. So really, this one goes with Green's theorem. So Green's theorem is for calculating. So let's do this one, 2 solutions. We will do it with a straight calculation of the line integral, and then we will calculate using Green's theorem as well. Right, so 131, calculate the line integral of g over c1. So g is y plus x, y minus x. Dot dr over over this same c. Or c is this, not over that. Okay, this is not conservative, right? Because p y is 1 and qx is minus 1. So that is not conservative, right? So we need a parameterization of this. So it's a circle of radius 2. So I'm just going to use the 2 cosine t, 2 sine of t, 0 less than or equal to t less than or equal to 2 pi. You have to pick a starting point and an ending point, but they're the same actually, and it doesn't matter which one you pick. Right? It's independent of parameterization. So the parameterization for a closed curve also depends on where you pick the beginning and the end to be, but it doesn't matter. So this is going to be, so that's r of t. So r prime of t is minus 2 sine t, 2 cosine of t, and f of r of t. So y plus x, so that's 2 sine t plus 2 cosine t, comma, y minus x, 2 sine t minus 2 cosine of t. Right, so the integral is equal to integral from A to B, f of r of t dot r prime of t dt. So this is integral from 0 to 2 pi. So f of r of t is that. I'm going to factor the 2 out. So this is sine t plus cosine t sine t minus cosine t dot. I'm going to bring the 2 out of that, so I guess it's a 4. Minus sine t, comma, cosine t dt. So what we get here for this dot product, so minus sine times that, so minus sine squared t plus cosine t sine t, minus cosine t sine t. And then multiply this by cosine, so it's plus cosine t sine t minus cosine squared t dt. So those cancel, and this just becomes minus 1. All right, minus 4 dt, so it's just 2 pi times minus 4. So minus 8 pi. Right? Now, that could also be solved using Green's theorem. Right? Green's theorem says the following. So if C is a simple closed curve in the counterclockwise direction, then, right, so C is simple closed curve, so it's just non-intersecting, just non-intersecting, no loop-to-loops, no disconnections, just a circle, essentially, a circle that's warped. Okay, so that's C in the counter. Oops, I got that in the clockwise direction, don't I? Then the line integral over C of P comma Q dot dr is the double integral, so that's C, over the interior of C, Qx minus Py dA. Right, so it brings the line integral it turns the line integral into a double integral, or the double integral into a line integral, whichever way you want to go. So here with this one, so that's C, and so the interior of C is just the circle of radius 2. So that's R, right? And so we're gonna, so via Green's theorem, we could very well use polar coordinates, but we're not even going to have to do that. It's the double integral over R, which is the interior of C. Right, so R equals the interior of C. So it's a double integral over R, Qx minus Py. So it's a double integral over R, and that's just minus 2 dA. So it's minus 2 times the area of R. There, that's a circle of radius 2. So that's pi r squared. So that's 4 pi. So minus 8 pi. Same answer. Same answer. Okay, so so we solved 131 in two ways. It's not a conservative vector field, so you can't use the fundamental theorem. But C is a closed curve, and when C is a closed curve, then Green's theorem might be able to help, right? Because it changes the line integral into a double integral over the interior of C. And the calculation was a little easier than this one, I think. Well, probably equally easy, these calculations. But, you know, I don't know, you might be sort of more like one over the other. So there's that. 131, 143. So find the circulation and flux. Oh, leave that out. We're not going to do flux integrals. So not for line integrals. We'll do them for surface integrals. So 143, we can omit that. All right. Going on to section 6.4, which is on Green's theorem. So we start with number 140. Let's see, table of, no, shoot, hit the wrong button. Green's theorem. There used to be this television show many, many decades ago. It was called A Different World. And on that show, so it was a bunch of kids that went to college, and on the show, the one character was a math major, and they did Green's theorem. And I mean, they butchered it, of course, but you know, at least they tried. So Green's theorem was there. So 140 is in the wrong, is not, that's in the previous section. Oh, I think we can just leave it out. 140. So 149, we'll just go to 149 here. So for the following exercises, evaluate the line integrals by applying Green's theorem. So in 149, we have, and they always present it in this P dx Q dy form. Sine x cosine y dx. Green's theorem is only for two dimensions. xy plus cosine x sine y. So that was number 149. All right, so calculate this, where C is as follows. The boundary of the region between the line y equals x and y equals square root x. So here's the line y equals x, and here's the line y equals, or the curve y equals square root x. And this is the point 1, 1, and this is going in the counterclockwise direction. If it was in the clockwise direction, you just apply Green's theorem and negate it, because the only difference, if you take the integral, line integral, vector line integral along the curve in one direction, if you want to do it in the other direction, you just negate the answer. So it's no big deal which direction it's in, really. So the interior of C right, is 0 less than or equal to x less than or equal to 1, and then x less than or equal to y less than or equal to square root x. So that's the interior of C as a type 1 region in 2 dimensions. So by Green's theorem, so this is P and this is Q. So the integral over C PQ dot dr equals, by Green's theorem, double integral over r qx minus py dA. So qx is y minus sine squared, no, y minus sine x sine y. Minus px is cosine x cosine y. dA. And isn't that sine x plus y? Not that that matters really, but well, no, I guess it will. Let's look up that double angle formula or angle sum formula. I think it's that. Whoa, that's not what I'm looking for. Although I appreciate the nice surprise. Yeah, sine x plus y is sine x. Oh no, that's sine x cosine y. It's cosine x minus y. So cosine x cosine y plus sine x sine y is cosine x minus y, which is the same as cosine y minus x. So this is the double integral over r, y minus cosine x minus y dA. So this is equal to the iterated integral, x to root x. Well, that's going to be nasty. Come on, hold on a second. QX y minus sine x sine y px cosine x cosine y. What's going on here? They want you to do that. Sine x cosine y. Cosine x sine y. It's not doable. I mean, it's I'm not sure what they're getting at here with this one. It's not a doable. Should have the answer on the back. 112. I mean, you're going to have cosine x minus square root x. And then cosine of 0. You can't do an antiderivative of cosine x minus root x. I don't think so. So this is dy dx. So antiderivative with respect to y is 1/2 y squared minus antiderivative of the cosine is minus sine, then you're going to negate it. So it's plus sine x minus y from y equals x to y equals root x dx. So this is equal to integral from 0 to 1, 1/2 square root x squared, so that's just 1/2 x, plus sine x minus root x minus 1/2 x squared minus sine of 0 is 0. So we got 1/2 x minus x squared minus sine x minus root x dx. You can't get the antiderivative of that. Sine x minus root x. There's no antiderivative that you can figure for that one. No, it's they're saying it's 1/12. It's not. Sine of x minus root x. it's gonna say something really weird. You know, there's the antiderivative. Whatever this means. C of this, S of that. S is the Fresnel integral, C is the Fresnel C integral. Okay, so Fresnel functions. So there's obviously a mistake in this thing here. So what number was this? We just did 149, so not doable. So can't calculate antiderivative. I didn't mark this one on the syllabus last time. Let me not forget to do it this time. 149, so that's a faulty problem. So there's a typo of some sort in here. So looking at a different problem, so that was 149, 151. So calculate the line integral minus y comma x. So that's that whirlpool. That whirlpool vector function. Minus yx, where c consists of the line segment from -1, 0 to 1, 0. So -1, 0 to 1, 0. Followed by the semicircular arc from 1, 0 back to, so the circle of radius 1. So all this in the counterclockwise direction. Right, so this is P and this is Q. So PY is -1 and QX is 1. So you see that that's not conservative. So via Green's theorem, this is the double integral over the interior of C. So let's look at the interior of C. So the interior of C as a polar region well, actually, I don't think we're even going to need that because this is going to be a constant. So this is qx minus py dA. So this is the double integral over r of 2 dA. So it's 2 times the area of r, which is just pi over 2, which is pi. Okay, if you were going to try to calculate this directly, what would you have to do? You would have to calculate the line integral over this straight line, and then calculate the line integral over the semicircle, and then add them together. Right? So, I mean, what you could do that. I mean, that's obviously a lot more work than doing what we just did right here. Very simple calculation. Sine x cosine y cosine x sine y. Qx is minus sine. Oh. Minus sine x sine y. Py. Oh, plus sine. No. Oh, I think I see what happened here in this problem. Qx is equal to y minus sine x sine y. Py is minus sine x sine y. I'm sorry, I made a mistake here. So Qx minus Py is just y. Sorry. So those canceled each other out. Right. So Qx minus Py is just y, right? So Qx is this minus this, and then I'm subtracting that, so this becomes a plus, and that goes away. So it's just y. Oh, okay. So that's a pretty nasty error on my part. So we can solve this for sure, very simply. So this is equal to the iterated integral from x to root x, 0 to 1, y dy dx. So integral from 0 to 1, 1/2 y squared, from y equals x to y equals root x dx. So it's integral from 0 to 1, so 1/2 x minus x squared dx. So this is equal to 1/4 x squared minus 1/6 x to the third from 0 to 1. So that's 1/4 minus 1/6. So least common denominator here is 12, of course, right? So this is 3/12 minus 2/12, so that's 1/12. Yeah, that's exactly what the answer in the back was. All right, so my bad on that one. So write things out carefully. That's the moral of the story there. So I think 167 looks like an interesting problem. Let's take a look at 167. Hint, you don't need that hint. So use Green's theorem to find the area of, oh, I see. Use Green's theorem to find the area of one loop of the 4-leaf rows r equals 3 sine 2 theta. So, wait, why Green? Use Green's theorem to do that. would you need Green's theorem to do that? You don't want to do that with Green's theorem. That would be an awful calculation. That'll be a horrendous calculation. What are they getting at here? 167, let's leave that one out. That's definitely not the right thing to ask for with Green's theorem. All right, 151 and 152 are the next on the syllabus. So we did this one already. Minus y, that whirlpool. Forget about 151. We were 151 on your own. So one thing that's nice about this vector field, where this is P and that's Q, and in this case Qx minus Py is just equal to 2. So by Green's theorem, so the integral over C of f dot dr, where C is closed, is equal to the double integral over r of 2 dA, which is 2 times the area of r. So C is closed counterclockwise. So the area in the interior of R is double the line integral over that vector field. And that's what's kind of cool about that vector field, is that it's related to the area, because the double this quantity just becomes 2. So if you want the actual area, you just divide by 2. So 1/2 of that vector field minus 1/2 y, comma 1/2 x. So that's 151, 152. So let C be the curve consisting of line segments from 0, 0 to 1, 1 to 0, 1 back to 0, 0. 0, 0, 1, 1, 0, 1. So this is the line y equals x right here. Right, so the interior, and this is all counterclockwise. So the interior of C, call it R, is equal to 0 less than or equal to x less than or equal to 1, and then x less than or equal to y less than or equal to 1. That's a type 1 region. Right? So x goes from 0 to 1, and then for any particular value of x, the y value goes from the line y equals x up to the line y equals 1, that horizontal line there. So by Green's theorem in 152, xy square root y squared plus 1 calculate the line integral over C f dot dr. This is P, that's Q. So via Green's theorem, this is the double integral over the interior of C, qx minus py dA, which is the double integral over r. Well, that's 0, and this one is just x dA. Right, so that's the iterated integral from x to 1, 0 to 1, x dy dx. So antiderivative with respect to y is just xy, so it's x times 1 minus x. So that's the integral x minus x squared. So 1/2 x squared minus 1/3 x to the third from 0 to 1. 1/2 minus 1/3 equals 1/6. Okay, so that's the, another nice application of Green's theorem. And as you can see, it saved us quite a bit of work there. If you were to calculate the line integral directly, I mean, first of all, you'd have to deal with this square root business going on here. But then you'd have to parameterize all three of the different lines here. This line, and this line, because the C consists of all three of those. So you'd have to do the calculation over the line y equals x, then do the calculation over the line from the horizontal line here to here, and then over this vertical line from here to here. So, I mean, that becomes tedious. I mean, it can be done. It's not going to be that bad because they're just, very simple lines. So the parameterizations are easy, but, this is definitely the easier way to go. All right, so that's 152. It's just a few more problems in this section. Well, they've got a bunch more, but, I mean, we're not going to do them all. I mean, there's not. It's a lot of the same sorts of things throughout all that section. So we'll finish up 6.3 next time, do a very quick presentation on 6.5, divergence and curl, and then get into section 6.6. We're definitely going to get into section 6.6 next time. 6.6 on surface integrals is long, okay, and the video lecture is like I've made it into 2 parts, and it's long. Okay, so you got to watch it and start on those problems. Get yourself familiarized, with what we have to do in that section. There's a lot of stuff going on there. Okay, but we'll definitely get into it next time. So we'll see you. Have a good weekend, and I'll see you on Monday. And email me with any questions or concerns.